Hi there. In my previous video I demonstrated using diodes mounted in TO220 package with electrically isolated tabs simply riveted onto some flattened copper pipe that has been soldered onto 22mm pipe. I showed the heat dissipation profile for the pipe horizontal in air and then vertical in air, allowing air to convect up the pipe. In this video I go a step further. Mounting the assembly in an insulated container using rock wool and a tin can surround, heating water in the pipe and relying on heat convection, adding an additional polyfuse in series with the diodes. This polyfuse also has been mounted intimately next to the top of the 22mm pipe. This is to limit the maximum current flow into the diodes to keep under their individual maximum power dissipations and effectively limit the water temperature in the outlet pipe to keep the water temperature to a tolerable washing temperature and definitely below boiling point. Water heating using sun is best done directly, e.g. solar panels that directly heat water or using evacuated heat exchanger tubes. These are great but are costly. There is additional insulated pipework required, pumps, controllers to cope with all eventualities, expansion chambers, antifreeze or flowback in freezing conditions. So, a cheaper alternative, though not the most efficient, is to use solar voltaic panels and just use wires to carry the power to the heating element in the water tank. It is inefficient to store electrical power from solar into batteries with controller conversion inefficiencies, then convert back from a battery through an inverter up to mains AC power again, with yet more inefficiencies, to only then dump that AC power into a standard AC mains immersion heater, though relatively easy to do. Ideally, you want to use the solar generated electricity to directly heat the water using direct current. You could just put solar variable generated DC into a resistive heater like a low voltage immersion heater, these are available, but beware, switching on and also off high current DC will blow up standard thermal switches that are designed for AC. Also, to match the most power to the heater, you need significant conductor cross-section to minimize cable loss. To get the most from the source and source impedance, you effectively need to vary the load impedance as the sun varies. This can be done with maximum power point transfer electronics, MPPT. An MPP tracker, but these add cost and complexity. You still need isolation switches, fusing, and temperature control electronics. Alternatively, we look here at a simple approximation that can be achieved by just using silicon diodes as heating elements, since their forward voltage drop can mimic being on the maximum power point if you match the diode drops to the solar voltaic maximum power voltage. Now, to do my characteristic testing to replicate connecting to the diode heating pipe, connected the spare heat exchanger coil in my tank. I connected a long plastic pipe from the top of the diode heating pipe to the bottom. There is a header tank, a plastic bottle of water. So the theory is the water is heated in the vertical pipe of the diode heating pipe. As the water heats, it rises and flows into the plastic loop pipe, and the water starts to cool and flow back down the plastic pipe to re-enter at the bottom of the diode heater, where the water is heated again. This natural water convection flow through the plastic pipe is intended to replicate the heat exchanger coil in my tank. I then started to take measurements, heating the water with various increasing levels of power, current, through the diodes, allowing time to stabilize, taking measurements of the temperature and time. I wanted to see what temperatures the water would reach and see if I had chosen my polyfuse carefully enough to limit water temperature and keep the diode heating in safe working zones. And I think this was achieved.